All right, welcome everyone. Today we're diving into one of the most interesting chapters in Class 11 physics, the mechanical properties of fluids. So here's what we've got on the agenda. We're going to start with the basics, what fluids and pressure are all about. Then we'll look at fluids at rest, and after that, what happens when they start moving. We'll even check out some real-world examples, dig into viscosity and surface tension, and then wrap it all up with a quick summary. Sound good? Let's get started. All right, first things first. Let's really nail down what we mean when we say fluid, and, just as importantly, how it's different from a solid. Okay, so the big difference here, the real key, is something called shear stress. Now, what is that? Well, imagine you're trying to slide your hand across the top of a table. That sideways force, that's shear stress. A solid, like the table, just pushes back, right? It holds its shape. But a fluid? Oh no. Even a tiny bit of that sideways force, and it just starts to deform and flow. And that's the whole reason why liquids and gases take the shape of whatever container you put them in. They just can't resist that shear stress. So, let's talk about pressure. This is like the most fundamental concept in this whole chapter. The formula is pretty simple. It's just force divided by area. But think about what that really means. Have you ever wondered why a sharp needle can easily pierce your skin, but if you push with the same force with the back of a spoon, nothing happens? It's all about pressure. That needle concentrates all that force onto a teeny tiny point, a very small area, creating a huge amount of pressure. The spoon spreads the force out, so the pressure is low. It's that simple. Okay, let's try this out with a real example. Imagine we want to figure out the average pressure on a person's thigh bones, their femurs. So first step, what's the force? Well, that's just the weight of the upper body, which is its mass times gravity. So 40 kilograms times 10 meters per second squared gives us 400 newtons of force. Easy enough. Now we just plug it into our formula. Pressure equals that force, 400 newtons, divided by the total area of the two bones. And when you do the math, you get a pretty big number. 200,000 pascals of pressure. That's a lot of pressure those bones are handling. Okay, so we've got a good handle on pressure. But what happens with pressure inside a fluid that's just sitting still, not moving at all? Let's take a look. This is where we meet a brilliant principle from the mind of Blaise Pascal, Pascal's law. It's super intuitive, actually. Imagine you have a water balloon, right? If you squeeze it in one spot, does the pressure only increase right where your fingers are? Of course not. The entire balloon gets firmer. That's Pascal's law in action. When you apply pressure to a fluid that's cooped up in a container, that pressure gets sent out, undiminished, to every single nook and cranny of that fluid. It's a perfect pressure-sharing system. So, you know that feeling when you dive to the bottom of a swimming pool and your ears start to hurt? That's this principle right here. The deeper you go in any fluid, the more the pressure builds up. And it makes perfect sense, right? It's because of the weight of all the fluid above you pushing down. So the total pressure down there, what we call the absolute pressure, is the pressure from the atmosphere at the surface plus the pressure from that column of water. And that extra pressure just from the water, we call that gauge pressure. It's the reason submarines need to be built so incredibly strong. So how do we even measure the pressure of the atmosphere around us? Well, here's a really clever invention for you, the mercury barometer. It's basically a balancing act. You've got gravity trying to pull this column of mercury down inside the tube, but at the same time, the weight of the entire atmosphere is pushing down on the mercury in the dish below. When those two forces balance out, the mercury stops falling. And the height it stops at, usually around 76 centimeters, gives us a direct measurement of the atmospheric pressure. So cool. Okay, let's go back to that submarine idea, but with some real numbers. Let's say it's 1,000 meters deep in the ocean. The gauge pressure alone, just the pressure from the water, is about 103 times the normal air pressure we feel every day. That is huge. And get this, on a tiny little window, maybe 20 centimeters by 20 centimeters, that pressure creates a force of over 400,000 newtons. To put that in perspective, that's like stacking more than 40 cars on that single piece of glass. Absolutely incredible. And this is where Pascal's law isn't just theory, it becomes a real-life superpower. I'm talking about hydraulic machines, like the lifts at a garage or the bricks in your car. Think about it. You apply a small force on a small piston. This creates pressure in the fluid. Now, because that pressure is transmitted everywhere, it also pushes on a much larger piston. And since pressure is force over area, the same pressure on a larger area creates a much, much bigger force. You're literally multiplying your force. It's how you can use your foot to stop a 2-ton car. It's pure physics magic. All right, we've talked a lot about fluids just sitting around. But what happens when they start to move? This is where things get really interesting. Welcome to the world of fluid dynamics. When a fluid moves, it can do so in two very different ways. First, you have what's called streamline or laminar flow. Think of a slow, gently flowing river. It's smooth, it's orderly, every water particle is following a nice, predictable path. But then, if you speed that river up or put a big rock in the middle of it, what happens? You get chaos, swirls, eddies. That's turbulent flow. It's messy, irregular, and much harder to predict. Now, this is a really cool and important concept called the equation of continuity. It's based on a simple idea. You can't create or destroy fluid as it's flowing, so the amount of fluid going into a pipe has to be the same amount that comes out the other end. So what happens if the pipe gets narrower? Well, to get the same amount of water through that smaller opening in the same amount of time, the water has to speed up. It's exactly what you do when you put your thumb over the end of a garden hose to make the water spray out faster. You're using the equation of continuity. Okay, get ready for one of the most famous equations in all of fluid mechanics, Bernoulli's principle. At its heart, it's really just the law of conservation of energy, but for a moving fluid. It tells us that for a fluid flowing along, there's a constant relationship between three things: its pressure, its speed, and its height. The key takeaway, especially for a fluid moving at a constant height, is this: where the speed goes up, the pressure goes down. And where the speed goes down, the pressure goes up. They have this inverse relationship. And this simple idea explains so much. So this Bernoulli's principle, is it just some fancy equation, or does it actually show up in the real world? Oh, it absolutely does. Let's look at a couple of amazing examples. First up, Torricelli's law. This is pure Bernoulli. Imagine a big tank of water with a small hole near the bottom. At the top surface, the water is barely moving, so its speed is low, but it has all that potential energy due to its height. When the water shoots out of the hole at the bottom, it's at a lower height, and the pressure is just atmospheric pressure. So to keep the total energy constant, all that potential energy gets converted into kinetic energy, and the speed it comes out with is exactly the same speed an object would have if you just dropped it from that height. It's a perfect energy trade-off. And now for the big one. How do airplanes fly? It's all about Bernoulli's principle. An airplane wing has a special shape, called an aerofoil. It's curved on top and flatter on the bottom. This shape forces the air traveling over the top to move faster than the air moving underneath. Now, what did Bernoulli tell us? Faster air means lower pressure. So you've got lower pressure on top of the wing and higher pressure underneath. And what does high pressure do? It pushes. That higher pressure below pushes the wing up, creating the force we call lift. That's what gets a massive jet off the ground. Okay, so up until now, we've kind of been talking about ideal fluids, which don't have friction or other tricky properties. But real life is a bit messier. So now, let's dive into two really important properties of real fluids: viscosity, which is basically fluid friction, and the amazing phenomenon of surface tension. Viscosity is a word you might have heard, but what is it? It's basically a measure of a fluid's resistance to flowing. Think about honey versus water. Honey is very viscous. It flows slowly. Water has low viscosity. It's like an internal friction within the fluid. And this friction creates a drag force on anything trying to move through it. There's even a formula for it, called Stoke's law, which tells us exactly what that drag force is on a small sphere moving through the fluid. Surface tension is one of my favorite topics. It's so cool. It all comes down to the forces between the molecules in a liquid. A molecule deep inside the liquid is getting pulled on equally by its neighbors in every direction. It's happy and balanced. But a molecule at the surface, it doesn't have any neighbors above it, so it feels a net pull inwards from the molecules below and beside it. This inward pull makes the whole surface act like a tight, stretched-out skin or membrane. It's why raindrops are spherical. That's the smallest possible surface area. And it's how some bugs can literally walk on water without sinking. Wow, okay, we have covered a ton of ground today. So, before we wrap up, let's do a super quick review of the most important concepts and formulas you'll need to remember. All right, here's your cheat sheet. These are the absolute building blocks. Remember, pressure is simply force divided by area. Pressure gets bigger the deeper you go. Pascal's law tells us that pressure gets shared equally everywhere in a closed fluid. The equation of continuity connects a fluid's speed to the area it's flowing through. The big one, Bernoulli's principle, is all about the conservation of energy, connecting pressure, speed, and height. And finally, Stoke's law gives us the drag force from viscosity. If you know these, you're in great shape. So, to wrap things up, I want to leave you with a little challenge. Now that you understand these fundamental principles, how pressure works, how fluids flow, start looking for them in your daily life. Seriously, when you see a curveball in a cricket match, or how smoke rises from a candle, or even just stirring sugar into your tea, you'll start to see the hidden physics of fluids at play. Where will you spot it first?